Just to briefly introduce myself, so I'm working with NXP as the... Can you actually see it?
No, yes, we can now. That's it.
I hope so.
Showing now.
All right, beautiful. Sorry that the camera is gone. As I said, the browser doesn't like me at all. So just as a bit of background, so NXP is a pretty large semiconductor company. So we've got 30,000 employees worldwide, but the headquarters are still in the Netherlands. Myself, I'm sitting in Munich. Lots of my colleagues are over in Hamburg as well, of course. And yeah, we basically provide processing power, connectivity options, security, and so on and so forth for a range of different sectors. We are pretty big in automotive, but there's also a growing and significant presence in industrial automation, mobile, smart home, and so on and so forth. So we are in this very interesting position that we try to look at the technology across different fields. And personally, I come from a background in collaborative robotics. So before I joined NXP, I was working on safety systems. So that makes it quite interesting to see how now AI is sort of moving throughout the whole field and changing things. And we can already see quite a few applications in industrial automation where machine learning is sort of emerging from the data centers and making its way closer to the application, closer to the assembly lines, the conveyor belts. So you'll often sometimes see vision systems which are already trying to pick up anomalies happening on the factory floor, things like package detection, QR code detection. I think that's pretty commonplace by now that you don't send up the data to the data center, but do that on the edge. We see increasingly people using visual defect recognition on assembly lines. Of course, there's also big things like voice and sound anomaly detection. So yeah, you have alarm analytics. For example, you try to figure out, is that breaking glass? I've got no idea why somebody would put baby crying on this slide. I hope you never have that in your factories. And of course, I mentioned anomaly detection. So that's a growing field where you do things like, especially in agriculture, where you try to identify pests out on the field, do quality control and analytics on the shop floor, motor performance, motor health supervision. Those are rising topics. And I think it's interesting to see how this sort of ties in with the waves of innovation in AI. So a lot of you are probably familiar with that, but let me just briefly recap. So in the late 40s, early 50s, we saw this first wave of AI rising, where we basically had a lot of the concepts we still use today established in academia. And then sort of interest dried up for a while. Then we saw the rise of the expert systems. So systems running in huge data centers and especially trying to filter database scale information. For a while, they couldn't deliver on the promise, so funding froze up again. And now we are sort of in the third wave, where we see deep learning, convolutional neural networks, massive data architectures. So recently, a couple of people have been sort of wondering, well, are we headed for another sort of downturn in this field? And there are some people asking, okay, where are my self-driving cars? Why are we still not flying on Mars? That sort of thing. So yeah, those are definitely justified concerns. There is a bit of a stall, I'd say, in the momentum of new algorithms coming up. However, if we look at the other side of the game, if we look at the actual compute devices on the field, we can see that these concerns are probably not that well funded. So just to sort of iterate over the last wave. So the first wave, that was basically a time where we did not have much compute at all. So a lot of that work was academic. It was more on paper than out in reality. Then the second wave, okay, we started seeing the compute moving from the data center, at least onto the desktop. So we started to see the rise of the PC, the personal computer. And then the third wave, well, there's an interesting thing happening there because suddenly compute was in everybody's pocket. We had cell phones which were connecting to huge data centers where you could crunch all that data. And what's happening now is that we start seeing the compute being divided far more widely, that we basically escape from the cell phone and at any waking hour are surrounded by devices which offer computation capacity. And I think this is really something which is going to drive the next wave. So there will be sort of like gradual migration over into a fourth wave where we will maybe change the algorithms, but I think the biggest change is actually that we are moving away from the data center out into the fabric which surrounds us in everyday life. So this is really going to stretch across all the verticals, from the consumer over the smart home, over mobility, of course, where we're looking at driving assistance systems, into larger scale connected systems like smart cities, smart industry, and so on and so forth. So today, of course, we are interested in smart industry. This is digital industry panel, so I'm going to focus my story a little bit on that. But I think it's sort of helpful to remind ourselves that AI grew in the clouds. So a lot of what we see today, a lot of the algorithms and a lot of the use cases, they are originally media-centered, where people upload large amounts of photos, for example, from their smartphones. They require data centers to do the processing. And that really gave rise to this ecosystem we see today with a bunch of big cloud operators, where we have tools which are mostly focused for designing algorithms and systems running on these large-scale data centers. We also saw a tendency towards heavy and powerful model architecture. So, for example, transformer models, those can grow pretty big. Now, as we sort of get out of the data center, as we move down below the clouds, where do we find ourselves? Well, it's a bit of a wilderness, and there are different rules at play here. And I want to sort of take a look at them over the next minutes. So we're going to see a lot more unreliable connections, for example. Everybody who's driven a car in the Bavarian countryside knows that you cannot rely on connectivity. So you need to bring your compute with you. You will face power constraints, especially when you're running on battery power or under thermal constraints. You will need to deal with far more unstructured and unpredictable environments. That's a lesson the guys in automotive learned early on. You'll need to make very real-time and robust decisions. So you really have one shot to get it right, and you need to get it right before something significant happens. And of course, you need to deal with far more hostile actors. So that could be people trying to spoof your system, but that could also be people just attaching a debug probe to your new system, to your new product, and just trying to download whatever intelligence you put on there and put that into their own system. So all of these are things you should take care of and think about early on. So another thing to think about, which edge are we actually looking at? So the cloud, I think everybody's pretty clear on. That's sort of like a pristine data center sitting somewhere in a protected space. Then one level below that, we have the network edge. So that's something which may or may not connect to the cloud, to the larger world. And it's what we, for example, commonly see in robotic systems, what we also see in car systems. And then, of course, there is the application edge, which, for example, if you're sitting at home, that could be your smart speaker. When you're sitting in a car, that could be the camera monitoring the road in front of you. So there we have different scales at which we operate. And now the question, of course, is why are we going out of the data center in first place? So Mark already sort of summarized a few of these. So we have the high round trip latency. So every time you want to talk to the data center, that takes time. And if you have a round trip of, let's say, 500 milliseconds, and you're driving in a car which is going 100 kilometers per hour, within those 500 milliseconds, you'll have traveled quite a stretch. So if you have something critical, you want to do it quickly, and that may require you to go on the edge. You oftentimes will find limited bandwidth, especially if you have lots of sensors connected. So if you have, let's say, 500 smart cameras in your factory, you don't want to pipe that all up to some remote cloud center. You may have, of course, limited connectivity, especially in mobile applications. So it's not only cars, but also think about AGVs, so automated guided vehicles. Think about drones, which may be flying over some fields. And of course, once you have a data center, you have associated cost, and there's also the issue of privacy. So whatever you upload can be intercepted on the way. So it makes sense to keep stuff which you want to keep private on the edge to start with. So where do we now place intelligence? So in a typical AI system, you'll find different stages. You'll oftentimes find some sort of pre-processing of raw data. Then you compute some sort of descriptor out of that, for example, using a convolutional neural network architecture. And attached, you'll find some sort of classifier or regression or, well, what have you. So we can, of course, basically take all of these steps and put them right on the application edge. That's what people oftentimes do with smart cameras, where you try to detect whether there's a defect in your product. That, of course, means that you need to package everything into this one device. But oftentimes, it's smarter to actually distribute things a bit further. So let's say you have a huge printing press, which you want to instrument. You start attaching, let's say, 50 vibration sensors to that press. So now you can start thinking, how do you actually distribute the intelligence? So for example, you could do a very first pre-processing right at the vibration sensor, then send up that data over the maybe slightly constrained bandwidth up to the network gateway. There you basically take the data coming from all the sensors, compute a descriptor, which is also time synchronized, which is another tricky thing to get right. And then you just basically send up that descriptor to the data center. And the data center maybe monitors not just one printing press, but 50 of them, or 100 or 200. And then you can basically take that reduced data and work classification, regression algorithms on that to get further insights. So really going to the edge, it's not a binary decision. It can be very gradual, but you of course need to make sure that your architecture and management complexity stays within manageable bounds. So just to sort of iterate, when you're running on the edge, we like to think in these sense, think, act cycles. So on the sensing side, you need to deal with far more noisy data, with weakly structured environments, which are also not very fully observable. Then when you run the inference, when you apply the intelligence you have to consider that you stay within your power budget, that you fulfill the real-time limits, that you do not go over the bandwidth you have available to communicate. And of course, once you decide to act, you need to consider that there's a single-shot success. If you fly the drone into the wall, the drone is gone. And you are obviously bound by the physics, and your action will change the world. So if you pick up a box, you need to recompute your maps of the environment, because the box which currently occupied the space is gone. So that really sort of has an impact on how you act. And well, sort of you need to make sure that you also think about security and safety much earlier than you would do in a typical data center application. So lots of different inputs into the design process you need to consider. I mentioned the local decision-making, which really comes from real-time constraints you may have or connectivity gaps, the unstructured environments you will encounter, security and safety. That's really crucial to get right, especially when you have an embedded system. You need to consider that whatever expensive model you trained, you put that on a chip and you put it out in the field. So if there's anything you can do really easily to increase your security, just start encrypting your model when it's not being used. Don't put your intellectual property out unencrypted. So that's like a very first hint to take. Also, something people often overlook, developer expertise. So you may have a great idea, you may have a great architecture, but do you actually find the right people on the job market right now? So that's also something to keep in mind. So enablement is very important. People tend to overlook dataset availability, especially in industrial applications. So when you are running a photo recognition engine on the net, you can sort of expect people to upload plenty of pictures with cats and dogs on them so that you can train. If you're running an assembly line, which turns out 100 pieces an hour, you just don't get that scale of data sets. So you need to make sure that whatever you plan, it can deal with the data set you have available. And of course, things like power constraints and overall system costs also figure into the whole design process. And yeah, then it's really the art of the system architect to find a good design balance between all these trade-offs. So some challenges to highlight. I'm just going to quickly, I already touched on some of them. So seam variability, dataset availability, that sort of goes overall into data model design. So you should have somebody who cares about that. Hardware design, that could be bill of material, power budget, the overall robustness of whatever you build. And that overlaps with safety. Safety is really, safety in AI overall, it's a much discussed but not fully solved field yet. So make sure that whatever you build, you stay within the grounds of the permitted, not within the bounds of what's possible. Because if you go to the notified bodies, let's say TÜV, and you cannot show them how your system is deterministic, you're going to have an issue with them. And of course, well, if you look at security, things like lifecycle management, overall IP protection, those are things you should definitely care about early on. So now if we sort of look a bit deeper into actually executing a machine learning model, we see that there is a sort of wide spectrum of applications and their needs. So on the low end, you have things like face recognition, which may be running in a doorbell, or maybe a bit more industrial face recognition running on a terminal of a machine, which basically only becomes active once somebody approaches. Simple speech recognition, that's pretty low end. You can do that on a microcontroller by now. On the high end, you have things like dealing with accents. So let's say you have somebody operating machinery with a heavy accent, and you need far more compute to deal with that. Real-time motion analysis of human bodies, that's a tricky subject. So you'll find that you may have very different needs for your application. There's really not one size fits all processor for AI, although in certain fields, especially autonomous driving, you start seeing certain packages which work well. But once you go to more differentiated applications, yeah, there's so many different things you can do. It's important to sort of have a continuum of processing options. So for us as a provider of chips, of compute engines, it's really sort of, we try to cover everything. Then we basically have some low-end stuff, which is in this case Cortex-M based. Then there is this crossover section where we have, it's still a microcontroller, but it's got far more speed and it's got far more connectivity options than you would normally see, far more peripherals. And then on the high end, we go into the realm where we have these i.MX processors, multi-core. We just had one new product, which is basically packing machine learning accelerator within the chip. So that basically gets you to 2.5 teraops, which is sufficient for basically dealing with accents and dealing with complex gestures, that sort of thing. Now, the tricky part here is to sort of get the enablement right. And that's also something people tend to overlook. So we come from the data center world and everybody's using the same tool chain. And when you need something, you basically just spin up another instance or spin up another Docker container. And you usually already have these very nicely laid out pipelines. I really have to give props to the cloud operators for getting that solved in a very nice way. Once you go for embedded systems, of course, the story is slightly different. So enablement is really important. And yeah, so we basically decided to go for different degrees of enablement. I know other companies are looking, some of them are looking at more integrated approaches, some of them are looking at more hands-off approaches. For us, we sort of try to strike the middle ground where we say, okay, if you know what you're doing, we have basic enablement where you can basically do your own design, start bring your own models and integrate that onto processors. Then we basically work with third parties, which can help you if you don't have that sort of expertise in-house. Of course, for a couple of simple things like voice recognition, Alexa integration, not that I expect to see that in a factory though, face recognition, we have sort of ready-to-play solutions where you basically just you get the blueprints, you get the bill of materials, and you can just go and integrate that into your system. And well, of course, then there's always automotive, which is living in a slightly different world since they sort of have different standards they need to comply to. So we needed to basically roll them their own enablement kit, which is now sort of integrating with the other EIQ tools. But it's really interesting to see how different levels of expertise need different levels of enablement. And yeah, covering all of that is a big challenge. All right, but to sort of get back to why we actually are moving to the edge. So just to sort of iterate quickly on the main point. So we really are going out of the data center because we want to have fast and dependable intelligence right on the edge. And we want to be independent from bandwidth constraints, so from intermittent connectivity. And of course, data privacy is a big driver. Now, I think a good webinar does not give you too many answers, but also lots of questions. And these are some questions you should start asking yourself when you think about moving towards the edge. So where do you really want to place what level of intelligence? Does it all need to be in the data center? Can you move some of it maybe into smart camera? If you distribute intelligence, how do you connect these elements? So how do you ensure that enough bandwidth is available? How do you make sure that security is certified? Yeah, and that's basically really the underlying part. So if there's nothing else you remember from this presentation, please take this away. Safety and security is not something you can attach later on. It needs to be something you think about from day one. And if you do that, you'll save yourself a lot of headache. And that goes not only for the edge, but also, of course, for the cloud, for the data center. All right, I hope I'm not too far over time, but yeah.